Hello again. In this video, I'm going to go over an example from section 3.8 where we find dy dx using implicit differentiation. Okay, so the example I want to look at is we have sine of xy is equal to x squared plus y, and we want to find dy dx. Now, we're not going to be able to find this using explicit differentiation because the first step in explicit differentiation is to isolate the y. And notice the y here is inside this sine function, but it also appears over here. And so it's not possible to isolate y. So we can't use explicit differentiation to find dy dx. So our only alternative is to find it using implicit differentiation. Okay, so the first step in implicit differentiation is to take the derivative of both sides of the equation with respect to x. And of course, these are still equal because we did the same thing to both sides. Okay, so let's find the derivative of this left-hand side. Now, if we're going to find the derivative of this left-hand side, we're going to have to use the chain rule because this is really a composition of two functions, right? The inner function is xy, and the outer function is sine. Now, there's two forms of the chain rule. Either one, you could use either one. I'm going to use the one that says dy dx is equal to dy du times du dx, but I don't want to use y because we have a y that appears in this equation, and I don't want to get those y's confused. So instead of y, I'm going to use v. But it doesn't matter. This is still true. dv dx is equal to dv du times du dx. And you can check that by seeing that these du's cancel out, leaving you with dv dx. Okay, so I'm using the chain rule here, except I'm replacing the y with a v. Okay, but it still works. Okay, it doesn't matter what letters you use, as long as the du cancels here, leaving you with dv dx, then this is completely legitimate. Okay, so having said that, remember the inner function here is the u, and u has to be written in terms of x, okay? So the inner function in this case is xy, okay? And then the outer function is the v, and the v would then be sine of u, right? Because u is equal to xy. This would become sine of u, and that's our outer function. Okay, so let's find dv dx. Okay, where v, of course, is the sine of xy, right? So, all right, dv dx is the same as dv du times du dx. Okay, so let's find dv du first. Okay, well, that's just a derivative of this sine of u, right, with respect to u, and that's cosine of u. Okay, and now we need du dx, which is simply the derivative of xy, all right, with respect to x, because that's what u is equal to, right? Okay, now if we're going to find this derivative, we're going to have to use the product rule because this is the product of x and y. Okay, and remember the product rule says you take the first times the derivative of the second plus the second times the derivative of the first. Okay, so the first is x. The second is y, okay, and we have to take the derivative of that, but we're doing it with respect to x. Okay, so we're going to get dy dx. Okay, so the first is x, and then the derivative of the second would be dy dx. Okay, plus the second function, which is y, and then the derivative of the first with respect to x. Of course, the derivative of x with respect to x is simply 1. Okay, so now we have the outer function, I'm sorry, the outer derivative times the inner derivative. Okay, so dv dx is dv du times du dx. Which of course is simply the outer function time, the outer derivative times the inner derivative. Okay, and then let's go ahead and replace this u. U is equal to xy, right? So this is really cosine of xy. Okay, and so that's the derivative of this left-hand side, okay? In fact, I'm going to go ahead and distribute the cosine of xy to both of these. Okay, so when you distribute it, you're going to get, x times dx, dy dx times the cosine of xy. Now remember, I can rearrange the order of multiplication. So I'm rearranging the order, okay? And then distribute it to the y, okay? And you get y times cosine of xy. Again, I'm rearranging the order of multiplication, which doesn't matter. Okay, so that's the left-hand side. Now, we need to find the derivative of this right-hand side, but we're allowed to break it up across addition. So we're allowed to find the derivative of the first one and then add it to the derivative of the second one. Okay, that's a property of derivatives. And of course, the derivative of x squared is simply 2x, right, using the power rule. And the derivative of y with respect to x is just dy dx. These are the same thing. Okay, and so the last thing we have to do is to solve for dy dx, because that's what we're trying to find here. The problem is dy dx appears in two different terms, this one and this one. So anytime that happens, there's a systematic way to isolate the dy dx. Okay, and here's how you do it. If you don't know how to do this, you can go in circles. So there's a systematic way for isolating the dy dx. What you have to do is you have to get all the dy dx terms, all the terms that have a dy dx in them, on one side of the equation, and all the terms that don't have a dy dx in them on the other side of the equation. Okay, so these are the two terms that have a dy dx in them. I want them on the same side. And so I'm simply going to subtract this one over to the left-hand side. Okay, and now I need the terms that don't have a dy dx in them on the other side. Of course, that would be this term here and this term here. Okay, so what I'm going to do is I'm going to subtract this one to the right-hand side. Okay, now I've separated them, right? The terms that have dy dx in them are on the left side, and the terms that don't have a dy dx in them are on the right-hand side. Okay, and then once you've done that, all you need to do now is to factor out the dy dx. Since it appears in every term on the left-hand side, you should be able to factor it out. Okay, so let's factor that out. And of course, that leaves you with x times the cosine of xy minus 1. Right, you're left with a 1 here when you factor that out. Okay, and that's equal to, the 2x minus y cosine of xy. Okay, and then now all we have to do is divide by this x times cosine of xy minus 1, divide that to the other side, and you'll get dy dx by itself. Okay, so dy dx would be 2x minus y cosine of xy divided by this term here, because we're dividing it to the right-hand side. Okay, so that's dy dx. Now notice that this derivative is in terms of both x and y, and I mentioned in the last video that will happen when you find dy dx using implicit differentiation. So unfortunately, our derivative is written in terms of both x and y, but the good news is we do have dy dx. It's just written in terms of two variables, x and y. Now, typically, when you perform explicit differentiation, we get the derivative in terms of x only. But with implicit differentiation, you'll find that the derivative dy dx will be written in terms of both x and y. And the only way to get rid of the y is to solve for y here, if that's possible. And of course, it's not. That's the reason we ended up using implicit differentiation instead of explicit differentiation. So we're stuck with this y. We can't substitute for it because we can't solve for it. We can't isolate it. Okay, so that's one example where you have to use implicit differentiation. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.